Yes, yes, I can see now. Thank you.
All right. So you're all welcome to today's meeting. So it's such a privilege to have every one of you join us in this meeting. Last week, we did a recap. Sorry, not a recap. We did a review, a critical review of this article. So before I go to the start section, I will just do the honor of doing a little bit of what we treated last week so that I can zoom to what we are expected to have today. Okay, so the paper we are looking at is the effect of the World Health Organization checklist on patients' outcome. So what these authors did was simple. They were trying to look at using the WHO surgical safety checklist, how effective it would be in reducing patients' morbidity and mortality. So the authors, they have two groups of patients. One, they expose them to an intervention or a treatment, which is using the WHO surgical safety checklist on them. Then the other group, they were not exposed to this treatment or to this checklist. And at the end of the day, they followed these patients over time and they decided to assess which group will have more morbidity, which group will have more complications, and which group will also have more death. That way, they could be able to hypothesize that the WHO surgical safety checklist is effective or not. So that's more like the summary of what this paper is talking about. And the study design that was used for this paper is the stepped wedge cluster randomized control trial. So this is a type of a randomized control trial, but it is slightly different from the original randomized control trial in the sense that there is another parameter added into it, which is the stepped wedge. Now, the cluster there is because they didn't use all the departments in the hospital. So they used some departments like the cardiothoracic, the neurosurgery, the orthopedic, the general, and the urologic surgical procedures or departments that perform these procedures. So these are the units they used. And these units could be a representative of all the other units in the hospital where they use, like the ophthalmology unit and the orthopedic unit and the rest of them. Okay, so in explaining this stepped wedge cluster randomized sampling, I would do that using a very simple example that I used the last time. But first of all, what is the actual randomized control trial itself? It is a type of a study design where you have two groups of people. One, you expose them to a treatment that you think is effective. The other group, you don't expose them to that treatment and you follow them over time to see which group will have the expected outcome. Now, for a step wedge randomized control trial, you do this assigning and follow up in batches. You don't do them all at the same time. Why for a randomized control trial, you do the assignment into whether this patient would be in the treatment group or whether this patient would be in the control group. You do that all at the same time. But for a step wedge, you don't do that all at the same time. You have a way of deciding which would be in what at different times. And that could be maybe you can do the selection every month. You can do the selection every 2 months. You can do the selection every 3 months. That way, the process will form some sort of a stepped wedge, something like this. So what the authors did, even if they were assigning patients to the treatment group and some to the control group, they didn't do that all at the same time. They followed a particular process, meaning they did the assignment in stages, maybe every 2 months, every 3 months, every 6 months, like that, until they complete the process. So it forms this shape that has this form of a stepped wedge. This white area is the control, and this pink area that has the SSC, which is the surgical safety checklist, is the treatment group. All right, so that is the study design. Now we go to the statistics itself. So for the table 1, what we saw here is that there was the characteristics of the patients, general characteristics of the patient, both for the control group and both for the group that was exposed to the surgical safety checklist. And what they did was a comparison of proportion or a comparison of means, depending on the variable that they are using. For example, in this first part that says increase in one procedure, if you see in bracket, that is a percentage. So the percentage for more than one procedure being performed on the patients for the control side was 19.6. And for the treatment group, which is the group that was exposed to the checklist, it was 10.2. As you can see, it shows that there were more procedures or more surgical procedures that were undertaken amongst those that didn't have the treatment intervention compared to those that had the treatment intervention. Almost 9 times increase in terms of the number of procedures. So now that we know that those whose treatment were not exposed to, we have more procedures performed on them. Is this 19.6 significantly higher than 10.2, even if the proportion shows that it is higher? In statistics, we don't work only by proportion. We work also by what they call evidence. Okay, so when we have these procedures and we are interested in determining if there is a difference, we don't just say, oh, 19.6 is higher than 10.2. We use some statistical procedures to do this. And those statistical procedures is what we call the test of significance. Now, you don't use the test of significance anyhow. The different tests of significance, there are different tests of significance for different comparison, depending on what you are comparing. So in this case, they are comparing proportions. They want to see whether 19.6% is significantly higher than 10.2%. So whenever you are comparing proportions and you want to see if there's a difference in the proportion, the recommended test is the chi-square. The authors refer to it as the Pearson's exact chi-square, which is here, and it is used for comparing categorical data, meaning data that generates proportion, and that is very accurate, okay? But I mentioned last week that the Pearson's exact chi-square may be a term that is unique if you would be using the statistical software for social sciences or statistical package for social sciences, which is the SPSS. I know when I do comparative analysis in SPSS, the term for the chi-square is usually Pearson's chi-square. But if I use another software, like I mentioned, like EpiInfo, you would not find the term Pearson's chi-square. Instead, what you would have is 3 forms of chi-square. That's what EpiInfo gives you. And the first form of chi-square that EpiInfo gives you is the uncorrected chi-square. Then it gives you the Mantel-Hansel chi-square. Then it gives you the Yates corrected chi-square. So what is usually recommended to use for your work is the Yates corrected chi-square. And that Yates corrected chi-square is equivalent to the Pearson's chi-square that is usually reflected when you're using SPSS statistical software. The Mantel-Hansel chi-square is usually recommended when you are doing a case control study. The uncorrected chi-square is usually not recommended because that chi-square has not undergone any form of standardization to check for confounding variables. That is why the Yates corrected or the Pearson's chi-square is recommended. So in this case, they use the chi-square to see if there is a significant difference between 19.6, meaning that will those in the control group have more or experience more procedure than those whose checklist was used on? Even if the proportion is higher, the answer is yes, because the evidence, which is the p-value, is less than 0.05. That's why at the p here, the authors had less than 0.001, which is less than 0.05. Now, less than or equal to 0.05, like we all know, is the cutoff for a comparison or an association to be termed significance. So in this case, I can boldly say that when a checklist is not used on the patient, that the patient can experience 9 times more surgical procedures performed compared to patients that the surgical safety checklist was used on. And my evidence is here, which is the P is less than 0.05. So that is statistically significant. Okay? Now, another thing I pointed out last week is that p-value is not the test of significance. The test of significance is the Pearson's chi-square. So I recommended that anytime you're doing an analysis and you want to represent your table in this form, please create a column for the test of significance. And the test of significance for this comparison between 19.6 and 10.2 is the chi-square. So you put the chi-square value, then you put the p-value. The p-value is needed because that is what gives you a clue whether your chi-square is significant or not, because the chi-square values don't have a range. So no matter what the value is, you won't be able to tell whether what you compared is significant until you see the p-value. But it's usually a best practice to include the test of significance before adding the p-value. And when you run these associations in any statistical software, it generates both. It gives you the test of significance and it also gives you the p-value at the side. So it's proper to have both. Now, in this other part, the mean age in years, this is the mean and the standard deviation. So what they did, they wanted to see whether there is a significant difference between the age of the patients in the control group and the treatment group. As you can see, the average age of the patient in the control group is 64.1, while for the treatment group is 54.3. So 54.3 is slightly lower than 54.1 is slightly lower than 54.3. That's roughly 0.2 lower, which may not be much of a difference. So that is why you can see that the p-value here is not significant. 0.869 is far higher than 0.05, so it's not significant. Now, for comparing means, what is the appropriate test of significance to use? The authors mentioned it here, the students, the independent sample t-test, okay? It's also called the student t-test. You use it when you're comparing numerical data, like you can see now, they're comparing numerical data here. They're comparing the raw average numbers. So that's why they are using the student t-test. So in this table one, that's fairly what the authors did. They just did a comparison of the different independent parameters between the control and the treatment group and see whether there's a difference. Okay, for the comparison for proportions, they use the Pearson's chi-square, while for comparing the means or the average, to average precisely, they use the student t-test. Because the student t-test is only used when you're comparing two average or two means. If you're comparing three means and above, you don't use the student t-test. You use what they call the F statistics, also called ANOVA, in full analysis of variance. So that's what you use when you're comparing three means and above. But for two means, the student t-test or the independent sample t-test is appropriate. Okay, so we went to table 2, where they looked at the morbidity and the mortality outcome of this randomized control trial. So as you can see, they also did a comparison between the control and the treatment group. The first thing they looked at was the number of complications, example, respiratory complications. So they wanted to see in respiratory complication, which group has more respiratory complication? Is it the control group or the treatment group? As you can see here, 6.4 is higher than 3.2 in terms of the proportion. So I can say that the control group that didn't have or experience the treatment have more respiratory complication compared to the treatment group. And they did what they call absolute risk reduction. In other words, control value minus treatment value will give you the absolute risk reduction. Although they didn't have the A arrow for so many of the variables compared, but if you look down here, they have for some. Like for complications, for the control group, they had almost 10 times more complication. Okay, sorry, 8 times more complication. So for the control group, you have 19.9. For the treatment group, you have 10.5. So 19.9 minus 10.5 will give you 8.4. So it means that the control group will 8.4 times have more complications, meaning that the use of the WHO surgical safety checklist could be very beneficial because it could reduce the complications by 8.4 times. So that is what this explanation means. So what is your evidence that 19.9 is truly and significantly higher than 11.5? That's the p-value here, which is our evidence. But the test of significance is the chi-square. So the p-value gives us a clue that our chi-square is statistically significantly different, meaning that there is evidence that 19.9 is significantly higher than 11.5. So that is what they did in the table 2. Although I advised that it is proper practice to also have the absolute value. In this case, they had just the percentages. But in your own case, when you'll be doing any form of analysis, please represent the absolute value, then in bracket you include the proportion, so that someone can actually have an idea what the number of the respiratory complication was for control and what the number for respiratory complication was for the treatment, and could calculate it and see if these percentages that you have here is appropriate. You know, it's good to make things clearer because of the phase of research that we are now called reproducible research, where people have the right to reproduce your work if they find it very beneficial. So the more information you have in your work, the more easier it is for people to reproduce your work. So that is it for this table 2. Then we go to table 3, which is where the authors have the logistic regression analysis that I was trying to explain last week. So I said that explaining this table might be slightly difficult the way it is, that I was going to show you something that is a bit clearer, then I will come back to this, all right? And so that is the same thing I would quickly do now. So I'm going to open a table from one of my published papers where I did a work on noise-induced hearing loss. Now, the exposure was loud sound by music instrumentalists, while the outcome I was looking for was how many of these music instrumentalists that were exposed to loud sound came down with noise-induced hearing loss. So my outcome variable was noise-induced hearing loss, and I did an association between social demographic characteristics of these individuals and the noise-induced hearing loss. So the noise-induced hearing loss, yes and no. Then the social demographic characteristics, I dichotomize them as you can see here. Now, for the first one, which is the age, I dichotomized my age into 2 groups, those that are greater than 35 years and those that are 35 years and below. So I looked at these 2 groups, which of them will have more noise-induced hearing loss, okay? As you can see from here, the overall number, I interviewed 216 respondents. The overall number of those that had noise-induced hearing loss was 85, and those that did not have noise-induced hearing loss was 135. Now, this number is quite high because the persons or the population where I collected this data from, they were those that were exposed to noise almost every day because they play instruments in their various churches. So that's why the number is quite high. Okay, and when the prevalence of those that have the noise-induced hearing loss was dichotomized, you can see that those that are older than 35 years, 56 out of the 85 had noise-induced hearing loss, which is 65.88. And 34 out of the 85 had noise-induced hearing loss for those that are 35 years and below. So you can see from this data that respondents that are older than 35 years had more noise-induced hearing loss compared to those that are 35 years and younger. And what is my evidence? The chi-square. My chi-square is 16.50 and my p-value is 0.001, which is less than 0.05. So we can see here that people or music instrumentalists that are older than 35 years will significantly have more noise-induced hearing loss compared to those that are 35 years and younger. So I went further to do the bivariant logistic regression. And the bivariant logistic regression gives us an idea of how much greater would this be. Why the chi-square tells you 65.88 is proportionally higher than 34.12, the odds ratio, which is the logistic regression, gives you a clue how much is the 65.88 higher than the 34.12, you see. So if I'm going to interpret my odds ratio, which is 3.34, my grammar will change. What I would now say is music instrumentalists that are older than 35 years are 3.34 times more at odds or more likely to experience noise-induced hearing loss. So you see, with the way this table is, it is clearer to actually tell which group has more noise-induced hearing loss or which group has less induced hearing loss, and the odds ratio and the 95% confidence interval is clearly written. Now, I would go back to the main article. Now, in the main article, look at this first line here. This first line, we have absence of the WHO surgical safety checklist, meaning absence of the WHO checklist. So they were seeing or trying to see if those that did not have, or those that didn't experience using the checklist, meaning the control group, will they have more complications? Because it's logistic regression analysis of complications. All right. So this is the dichotomized variable, absence of the WHO checklist, and after. After means the use of the WHO checklist. This is the number, and this is the odds ratio, which is 1.91. So if I'm going to interpret this, the interpretation would be patients that didn't experience the treatments, which is the WHO surgical safety checklist, will 1.91 times more likely to have complications during surgery. And my evidence is what? Statistically significant. So that is the interpretation for this. As you can see, they have unadjusted and they have fully adjusted. So the difference is, for the unadjusted, you don't check for confounding variables, because not everything here could be independent on their own, even if they are called independent variable. But because they may all likely be found in the same patient, they might be confounding each other. So even when you have done the unadjusted, you should also do the fully adjusted, which is the multivariant. Now, I would explain this to you using my work again. Now, if you see, I did an association between the social demographic and the noise-induced hearing loss. And apart from the age, I also used sex. And the sex is showing that males were 15.14 times more likely to have noise-induced hearing loss. This table also showed that those that are married, because our interest is in the value that is up, that's how it is done. Those that are married are 2.42 times more likely to have noise-induced hearing loss. And also those that have tertiary education are 3.30 times more likely to have noise-induced hearing loss. Now, this is unadjusted. I am very convinced that some of these independent variables could be serving as confounders, meaning they are not true independent variable in this model. So apart from doing this first bivariant, where I compared the bivariant variables one by one, I did age and noise-induced hearing loss, sex and noise-induced hearing loss, marital status and noise-induced hearing loss, educational status and noise-induced hearing loss. I went further to also put all of them in a multivariant pool, which is now the adjusted odds ratio. So I didn't just decide to trust this. Because look at it this way. Someone that is older than 35 years will most likely be married and will most likely have tertiary education. So it may not necessarily be because they are married, that's why they have noise-induced hearing loss, which is what this table is showing. Or because they have tertiary education, that's why they have noise-induced. It could just be because they are older. So being older means they will likely be married and likely have tertiary education. So these results may not be a true representation of what is happening. That is why you need to do the multivariant to adjust for confounders. So when I did the multivariant, this is what I had. You will see that marital status and education were not significant anymore. Like you can see, are you seeing the p-value? Up here, marital status was significant. You see the p-value? Educational level was significant. You see the p-value? But when I put everything in a pool to check for confounder, they were no longer significant. Marital status was not significant anymore. Education was not significant anymore, meaning that the reason why it was looking like those that are married and those that have tertiary education will have more noise-induced hearing loss is because someone that is older will likely have been married and will likely have had tertiary education. So you see marital status and educational level, they are confounders. If I didn't do this multivariant logistic regression, I will go around giving people the impression that once you're married, be ready to have noise-induced hearing loss. Or once you have finished tertiary education, be prepared because noise-induced hearing loss is coming on your way. That would be a very wrong representation of my data. So adjusting for confounders saves you this so that you don't interpret your work in a wrong way. All right, so let's go back to what the authors have done. And that is the same thing they did. So after doing the unadjusted, they did the fully adjusted. So now they have found out that those in the control group, we have almost 1.91 times more odds of having, meaning they would have complications more than those, more than the treatment group. Now, once all these independent variables were put in a pool, they were checked for confounding, you will find out that the odds ratio even increased. So when it was tested for confounding variable, it even increased to show that this variable absence or presence of WHO SSC is truly independent and is not influenced by any other variable. So because the unadjusted and the adjusted is significant, I can truly say that those in the control group that did surgical procedure without the use of the WHO surgical safety checklist will have more complications, will have at least 1.91 or 2.01 more complications than those in the treatment group. So from this result, I would recommend that the WHO surgical safety checklist should be utilized, should be used, because both my unadjusted and my fully adjusted has shown that that variable is truly, truly significant. And so policymakers and stakeholders should pay attention to ensuring that there is thorough or critical or full implementation of the use of the WHO surgical safety checklist. And I want you to appreciate that randomized control trial is at the top of evidence, meaning that you have the first one, you have the case series, and you come down to the cross-sectional, you come down to the case control, you come down to the cohort, then you come down to the randomized control trial before you begin to go into systematic review and umbrella review. As these study designs grow from case series, cross-sectional to randomized control trial, the stronger the evidence. So meaning that I would trust a study that is a randomized control trial more than a study that is just a cross-sectional study. So because this study is a randomized control trial, it means that I can rely on it for evidence, because the evidence of the randomized control trial study design is very high, okay? The second one is the sex. As you can see here, it shows that this is showing that male patients have more complications. You see, male patients have more complications. See, how many? 1.32. Are you seeing it? And this is significant. But when they did the multivariant, did you see? It was not significant anymore. Telling you that age is sex is a confounding variable, meaning males will not likely have more complications than female. The unadjusted is looking that way and telling us that way. But when you test for confounding, it's not significant anymore, so that you will not go around saying that males will have more complications during surgery, because the adjusted value or the adjusted p-value is showing that there is no evidence, so because the p-value is not significant anymore. So we cannot use sex as a judgment for complications from what this study is saying, all right? So I think that is briefly what happens if you go down. Even if you look at the surgical specialty, the p-value is significant, but if you're looking at the odds, you will see that cardiothoracic patients in the cardiothoracic department have more complications compared to patients in neuro, general, and urology. You see, patients in cardiothoracic, 8.4. So patients in cardiothoracic are 8.40 times more at odds of experiencing complications. While those in neuro is 1.2, those in general is 1.24. And the evidence is significant. And even after adjusting, it is still significant. All right, and it didn't decrease much, 8.4, 8.15. So that is to tell me that between these departments that were measured, those in the cardiothoracic unit had more complications compared to patients in other units. So that is what table 3 is saying. I think that is the last table. In conclusion, with regards to this article, I can say, because the randomized control trial is a higher evidence, I can say for sure that the authors were able to prove in this work that the use of the WHO surgical safety checklist is very beneficial, because the logistic regression analysis, both in the bivariant stage and in the multivariant, after testing for confounders, still shows that the group that didn't have the benefits of having the WHO surgical safety checklist being used on them will have more complications compared to the group that have the benefits of having the WHO surgical safety checklist being used on them. Okay, thank you. Thank you very much for listening.
Thank you so much. If there are a few questions coming in, so I'll just tell the other participants, if you have questions and you've not yet posted them, please post them in the chat box. Let me read out the first one. Somebody said, I wish to fully understand the terms adjusted and unadjusted.
Okay. All right. So the term adjusted and fully unadjusted is simple. You can say unadjusted and adjusted. You don't really have to add the word fully. Okay. Unadjusted means the logistic regression has not been tested for confounding variables, and adjusted means it's been testing for confounding variables. The reason why you need to test your logistic regression for confounding variables is not to fall in error, like the example that I showed here, where my work in the unadjusted form is showing that being married and having tertiary education will predispose you to having noise-induced hearing loss, which is not really true. The reason why being married and having tertiary education is showing that is simply because those that are older which will likely have more noise-induced hearing loss, will likely be married and will likely have tertiary what? Education. So when I adjusted for confounders, in the bivariant, you put the two variables at a time, meaning you put the independent variable, example age, and the dependent variable or the outcome, example the noise-induced hearing loss, in the bivariant analysis pool, one at a time. Age and noise-induced hearing loss, one at a time. Sex and noise-induced hearing loss, one at a time. Marital status and noise-induced hearing loss, one at a time. That's how you do them, and you calculate for the odds ratio. But in the multivariant, when you are now testing for the confounding, you will put all the variables inside the pool and run the analysis and see whether the variables that were significant before, if they will still be significant. If they were significant before, like in this case, marital status was significant, educational status was significant, but when I adjusted for confounding, they were not significant anymore. Marital status was not significant, education was not significant, meaning that they are confounders. They are not truly being significant. Another good example I can give is men that smoke. Someone that smokes and you walk in a nightclub where other people smoke, and you did a study of people that smoke and see whether they will develop lung cancer. Notice that already working in an environment where people smoke is even a greater risk than even the smoking itself. So when you do a bivariant logistic regression to see whether those that smoke will most likely have lung cancer, also put the variable if you are working, which environment you are working, because that could also be a confounder, meaning that the risk of the person that smokes having lung cancer was probably increased because they work in that environment, not necessarily because they smoke. So when you put it in a multivariant logistic regression, multivariant means more than one variable at a time, you may now begin to see that, oh, this guy smokes, but he truly didn't have lung cancer. I think what increased his susceptibility to lung cancer was the fact that he works in an environment where almost everybody smokes, not because he smoked himself. I'm just giving this as an example. So that's the benefit of adjusting. You adjust for things that may influence the result and make it look like it is high when truly is not. All right, so that is the difference.
Thank you. He's
All
commented that it's very clear, so thank you very much.
All right.
Then there's another question. Somebody said that, can you please comment on age in your own multivariate logistic regression model? I think he's talking about your own study.
Okay, so in my own study, what I did was, if you look at this, I dichotomized the age, because from literature, you would see that age itself, as you get older, your hearing drops. I mean, from literature, that's what literature shows. And being exposed in an environment where you always listen to loud music increases that risk. So what I tried to do was to check whether those that are older in a particular age, so I did some kind of a cutoff using my average per se. If you check in this case now, you will see that the average of the people or the respondents or the musical instrumentalists that have noise-induced hearing loss is 36. So meaning that my cutoff is around this point. So I did a cutoff around this point, so which is greater than 35. That's 36 and above. That's the cutoff from my average. That's if you don't find a standard cutoff in literature, you can use the average age to do your cutoff. That's usually recommended. So I used my average age here to do my cutoff. So I had 35 and below, then I had 35 above, meaning 36 and above. And I checked whether those that are 36 years and above will likely have more noise-induced hearing loss. And that is what my study showed. You see, those that are greater than, that are 36 years and above, you see, 65.88. Why 35 years and below, 34.12. Why 65.88 is greater than 34.12? I need evidence, because in research, you don't just say, oh, 65.88 is greater than 34.12. No, you need evidence. And what is the evidence? The evidence is the test of significance. And what test of significance should I use? Chi-square, because I'm comparing proportions. So I use the chi-square, which is 16.50, and my p-value, which is less than 0.05, is showing that those that are greater than 35 are truly significantly higher in terms of being susceptible to noise-induced hearing loss. And I did the logistic, which is the odds ratio, that showed that they were 3.34 times more likely to have noise-induced hearing loss compared to those that are younger in age. So that is what I did.
Yeah, thank you. Somebody asked about if you could just say a little about the meaning of a confounder.
Okay, now a confounder is simply something that makes your work, or something that makes the variable that you're comparing looks good, or looks or appears to be significant when it's truly not significant. That is a confounder. A confounder is something that will make that variable looks as if it has a greater risk when truly it doesn't. But because there's so many things inside, that is why it's looking that way. So a confounder is like a bias, something that biases your work, makes it look like, oh, this is how it's supposed to be, when truly it's not supposed to be. Like in my own work, it's looking like those that are married will 2.42 times more likely to have noise-induced hearing loss, when that is not true, in the sense that the only reason why these married people have more noise-induced hearing loss is because the people that are older than 35 years, which have more noise-induced hearing loss, are most likely married and are most likely have finished secondary school, are in their tertiary level of education. Not necessarily because having tertiary education will make you more susceptible to noise-induced hearing loss. It's just the age thing, because being married and having tertiary education is a factor of age. You see, so they are confounding variables. They are not true independent, meaning that a confounder is like a variable that cannot stand on its own. It is hiding inside something. So the marital status and education is hiding, okay, inside the fact that these people are older in age. When you put them on, when you now put them in a pool, you will now find out that they are on their own, they can't stand the test of time. So that is what a confounder is. It's just simply something that looks good by hiding inside something, but on its own, it's not really the way it is. Like the example that I gave to you. If you are assessing someone for smoking and see whether they will have, okay, like another example I could give using this my work is when I was recruiting those that play musical instruments, there are 3 groups of people I didn't add that would have been a confounder to my work. The first group of people I didn't add were those that are older than 50 years. I didn't include them because being 50 years alone and above, I mean, even if you are not playing musical instruments, your hearing will not be like someone that is 20, 30 years. The second group I didn't include are those that work in noisy environments, those that work in construction sites, those that work in airports. Even if you don't play musical instrument, the fact that you work in these 2 environments is already making your ears not to be healthy. So now adding the musical instrument will now look like your ear is so terrible when even playing in church was not really the reason why your hearing was not good. Is because you work in a construction site and you also work in an airport. So these things were confounded. And the third one, I didn't include those that have a history of ear disease, because having ear disease alone already makes you susceptible to noise-induced hearing loss, not even playing the musical instrument. So that's what a confounder is. A confounder is something that may make something look terrible or look higher in terms of proportion when there's no reason to be so. So you have to fish them out so that you can see the true picture of the independent variable that you're measuring.
Thank you so much. There was a question from Brian, but you had answered it whilst you were addressing the first question. He wanted you to comment on the final model, but I think you had addressed it whilst you were addressing the first one, except if you have anything else to say about it.
No, I don't have. You know, I actually sent you a message to confirm from the authors, you know, why do we really have the final model? Because it's supposed to be the unadjusted and the adjusted, which is the bivariant, the multivariant. So the role the final model is playing is not really quite clear to me, but I am assuming that it will be part of the multivariant. You know, I am assuming, yeah.
He didn't reply the mail, but if he does, I'll post his response on the group.
Great.
So thank you, everybody. I think we've addressed all the questions, and you have a lot of, your approval rating is very high from all the comments in the chat box. So thank you, everybody, for attending, and we're hoping to have another session next month. So
thank you.
bye.
Bye.
Thank you so much.
Thank you.